This video is presented to you by Rajiv Institute of Technology, Hassan, Department of VLSI Design and Technology. I am Mrs. Ambika K, working as Assistant Professor. In this video, you are going to learn about the fourth experiment of Digital Logic Circuits Lab, which is design and implementation of 1-bit and 2-bit magnitude comparator using basic gates. The first component is 1-bit magnitude comparator. Magnitude comparator is a combinational circuit which is used to compare the magnitudes of two binary numbers. And in this section, you are going to learn about a 1-bit magnitude comparator. Means we have to take two binary numbers. Let us consider those two binary numbers as A and B, and the length of each binary number is 1. A is having 1 bit, B is having 1 bit. And whenever comparison is performed between any two numbers, always there is a scope for three outputs. One is greater than, second one is lesser than, and the third output parameter is equal to. According to that, we are going to prepare a truth table. So in this truth table, for the two inputs, we are having four different combinations: 00, 01, 10 and 11. And we are having three output variables: A lesser than B, A is equal to B, and A greater than B. For the first combination, where A is equal to 0, B is equal to 0, both the numbers are equal. So the output variable A is equal to B should have a high value. The remaining two output variables, they are supposed to show 0 value. For the next combination, 0, 1, A is equal to 0, B is equal to 1. So it's evident that A is lesser than B. So that output variable should have a higher value, the remaining two 0. Third combination, A is equal to 1, B is equal to 0. Here A is greater than B. So that particular output variable will have a logic 1 value. The last combination is A is equal to 1, B is equal to 1. It means both A and B are equal to 1. So that output variable value will be equal to 1. The remaining two output variables, they are having a logic 0 value. From this truth table, with the help of K-map, equations have to be derived. So K-map is used for the purpose of simplification of Boolean equations. So after simplifying, we will get the expressions for A greater than B as A B bar, A lesser than B as A bar B, and A is equal to B. This is an exclusive NOR operation. And this is the logic diagram which corresponds to 1-bit magnitude comparator. So three output variables: A greater than B, A lesser than B, and A is equal to B. A greater than B, A lesser than B, they will make use of AND gate and one NOT gate, whereas A is equal to B, this is going to take the help of an exclusive OR gate followed by a NOT gate. The next section is 2-bit magnitude comparator, which is a slightly higher kind of a circuit. So in 2-bit magnitude comparator, we are going to compare two numbers. One is A, another one is B, and the length of each number here is 2. So A is having the bits A1, A0, and the number B is having the bits B1 and B0. The output variables are as usual 3: A greater than B, A lesser than B, and A is equal to B. So here altogether at the input section, we are having four variables: A1, A0, B1, B0. Since the input variables are 4, we can expect 16 different combinations. The first combination is 0, 0, 0, 0, and the last combination is 1, 1, 1, 1. For all these 16 combinations, we will get the output accordingly. So this is a truth table which has been designed depending upon the working of 2-bit magnitude comparator. From this truth table, the equations we are going to derive. So we are taking the help of K-map in order to simplify the equations. After the simplification, we will be arriving at the equations for A greater than B is equal to B and A lesser than B. And for these equations, This is the logic diagram. So this logic diagram, it is constructed using basic gates. We have taken the help of exclusive OR gate. Now we are doing the demonstration of 1-bit magnitude comparator. According to the logic diagram, we require here 3 ICs. One is AND gate IC, that is 7408. Then OR gate, the corresponding IC is 7432. And we require one NOT gate also as an inverter. So for that we are taking 7404 ICs. So these 3 ICs are mounted here. This is 7408, 7404 and 7432. So these 3 ICs are mounted on their sockets. Now we have to make the preliminary connections of power supply and ground. As we know it earlier, 7th pin has to be connected to ground and 14th pin should be connected to VCC. For all the 3 ICs, the same connections should be done. 7th pin connected to ground and 14th pin connected to VCC. Then, since it is a 1-bit magnitude comparator, we require 2 input terminals. One is A, another one is B. Let us consider this as the input terminal, input variable A, and this as the 2nd bit input variable B. And whenever we are doing any comparison, obviously there are 3 output. One is greater than, another one is lesser than, and third one is equal to. So let us consider these 3 as output variables. Let us consider this as A greater than B, this as A lesser than B, and the third output as A is equal to B, and we have to keep remember. So this is A greater than B, this is A lesser than B, and this is A is equal to B. These are the 2 input terminals. We have rigged up the circuit for 1-bit magnitude comparator. After rigging up the circuit, let's turn on the IC trainer kit. Always make sure that only after rigging up the circuit, trainer kit should be turned on. Otherwise the ICs are going to get heated up and they will get damaged. The trainer kit is turned on. Now let us verify the truthfulness of this circuit with the help of the truth table. So according to the truth table, for the combination of A and B as 0, 0, A is equal to 0, B is equal to 0. So the comparison is going to say that these 2 bits are equal. So this is the equal output variable, and this output is showing high value. So when both A and B are equal to 0, 0, this output is glowing. Similarly, the same situation occurs when A is equal to 1, B is equal to 1. So the output variable A is equal to B is glowing, which is high. Let us check the circuit diagram for the other 2 combinations, A greater than B and A lesser than B. Let us first go for A as 0, B as 1. A is equal to 0, B is equal to 1. It clearly states that A is lesser than B. And the middle output we have kept it for A lesser than B. So it is having a value high. The next combination is A is 1 and B is 0. A is 1, B is 0 means A greater than B. So this is the output variable that we have taken for A greater than B. So all the 4 combinations are verified. Let me check once again. 0, 0, A is equal to B. 0, 1, A lesser than B. 1, 0, A greater than B. 1, 1, A is equal to B. So all the 4 combinations of this 1-bit magnitude comparator, they are verified.